Application of post-tensioning in building construction. Post-tensioning has been used in building construction in many ways. I have compiled a number of applications which I believe are of interest to you, and I'm going to present them one by one. I talk about the specific feature of each of the applications and also show you the construction style used in each. I talk about flat slab construction, the hardware used, hardware systems available, flat slab, podium slabs, beam and slab construction, ground supported construction, mat foundation, slab on expansive soil, and industrial slabs, industrial floors, transfer floors, repair and retrofit. Now, coming to the hardware has as its core the strand, 7-wire strand. Now, the 7-wire strand, if greased, covered with grease, and encased in a plastic coating, as I show here in the center, this is the unbonded system. If a number of strands, one or more, are encased in a sheathing, and the void in between is later grouted such that the strand forms a permanent bond with the grout, and through the sheathing with the concrete around it, that is the bonded system. We have the unbonded system and the bonded system. In the unbonded, the strand is free to slide within its sheathing, whereas in the bonded system it is not. Here is an example of an unbonded system. Each of these are 4 or 5 strands, 4 or 5 tendons next to one another. And then on the right we have example for a flat slab construction of a grouted system. Each of these metal sheet ducts contains 4 to 5 strands. Here we have a slab reinforced with unbonded tendon, ready to receive concrete. On the right, it is a similar construction using grouted system, left unbonded system and the right grouted system. Both of them are flat slab construction. Column supported constructions are very common. The one you see is in San Francisco, where we have the highest seismic exposure. To the right is one in Florida, where we have one of the highest wind exposure. I have selected these two to demonstrate that application works well both in high seismic and high wind construction. High rises, these are medium rise, unbonded in California around 14 levels. The other application, which is very common in the US, is a podium slab construction, where you have a different occupancy above a certain level to what is below. It makes sense to put a transition slab between what is above and what is below. Here on the left below, I have retail and parking, above residential. On the right again, you have parking first, and then there is, it's all parking, and then above residential. The support layout of the upper levels typically is different with that of the lower level. As it is shown here, the load from above comes in the interior of the span. So the slab has to be designed recognizing the loads from above not being directly on the level below. The typical construction is 4, 5, and now even 6 levels above podium slabs. If it is 10, 12, or more, there's a different construction, which will be transfer plates. On the left, you see the retail on the ground level and residential above. The top of the ground level is a podium slab. Here, the top I am showing with my pointer is a podium slab, and above is a different type of a construction. The architectural arrangement above is different from that below. Next, I have beam and slab construction, typical of parking structures in the US, where the slab is post-tensioned in one way over the beams that support it. The right shows a parking structure, San Jose Airport in California, using unbonded tendon with the type of construction shown on the left. Now, let us look at ground supported slabs, post-tensioned ground supported slabs. I have identified 4 major categories. 1, slabs on expansive soil, industrial slabs, mat foundation, and sports grounds. Let us start with slabs on expansive soil, the largest application of post-tensioning in the US, where the soil that supports a light structure like a 1-level, 2-level, or maybe 3-level residential or a light industrial has a lot of expansive soil content, changes its volume depending on the moisture in winter and summer. It is common to use a post-tensioned slab to take care of the seasonal change, to control the deformation of the structure above the slab, which could have been induced by the soil below. Now, one option, one scenario is what I have on the right. In summer, where moisture is reduced, there can be loss of volume around the perimeter and separation of the slab from the ground, referred to as center lift. Rise in temperature, as shown at the bottom right, results in lifting the perimeter of the building. The actions of center lift and edge lift result in deformation of the slab. The objective of the slab design is to limit the deformation and make the deformation acceptable for the structure above it, reduce the level of a deformation to an acceptable limit. Now, here I have the example of edge lift where rise in the level of soil around the perimeter lifts the corner of the slab. What we have is a deformation delta over length L. Past L, the impact of the soil movement is not of significance. The target of design is to have delta over L, within an acceptable range in winter and in summer, where there is a fall, a drop in height of the perimeter. Again, you will have a delta deflection over an effective length L. Delta over L has to be manageable, acceptable for the structure above. Here I am showing you a slab on grade being reinforced and ready to receive concrete. The concrete is cast on the right and it's ready for a superstructure. Typically you have two sheets of plastic and then tendons which run parallel to one another in one direction and parallel in the orthogonal direction. In some parts of the US, the construction is that includes ribbed beams between the perimeters. This is not practiced in California, but elsewhere it is. What you see on the right is in Brazil, from Brazil. The reason I show it is the method in which they put the reinforcement, they arrange the reinforcement. I found it of interest. They use these supports so that the reinforcement will be at a high, which is convenient for the technicians to tie the tendons together and also to put the supports at intersection of the tendons. When they are done, they will then remove these supports and the reinforcement falls on the ground and they cast. Example on the left is one in which waffle voids are used. Between each waffle over the stem or in the stem there is one strand. That's another style of construction using ground supported slab. Next, industrial floors. Industrial floors are those that you do not like to look like what I am showing you on the screen. You want a crack-free floor, even, smooth surface, where you have forklift trucks with high value weight lifting many levels as shown here on the right. You do not want the hoist here to tilt. So the objective is to have a smooth, crack-free surface, jointless, and ability to support concentrated loads. There, post-tensioning helps to delay the formation of cracking. I have shown here the concentrated load typically results in tension at the bottom, compression at the top. The application of post-tensioning results in reduction of tension at the bottom and thereby delays cracking. And if there isn't cracking, delays its reduces its width. Here is example of an industrial floor using unbonded tendons. To the right is industrial floor using grouted tendons. What is always critical is the construction of industrial floors, where in casting the slab is typically subdivided into smaller regions, 40 meter, 120 feet, about this length, in order to reduce the loss of prestressing in the slab due to friction between the slab and the support. Typically, 2 layers of plastic sheet are used over the soil, and in some applications, a lubricant is sprayed between the 2 sheets. The objective is to reduce the friction coefficient, which could be as high as 1 or even more between the soil and slab, to something like 0.4, 0.3 to save post-tensioning. On the right, I show a slab which is subdivided into casting regions. Here the first region is pulled at both ends, is about 80 feet. But the next one, which is being pulled at one end only, is obviously smaller in width. This is very critical in construction. Now, next is mat or raft foundation, where the allowable soil pressure is low, and you have also likelihood of high settlement. The conventional thin mat may result in higher soil pressure below the concentrated loads from above. One option to improve the distribution is to increase the foundation thickness. That improves the distribution. The other option is to select post-tensioning and profile it such that it will lift the load from above and transfer some of it away from the point of application of load from above. So you get typically a better distribution, slab thickness will be reduced, and in general, the total reinforcement will be less. There will be saving in reinforcement as well as in concrete. Here is an example using grouted tendons ready to receive concrete. These depressions that you see are locations of columns from above. Another example where below the column from above we have the tendons going down to pick up the column load. Here unbonded tendons are used, and on the left bonded tendons are used. Next, transfer plates, where a large number of levels with smaller spans are supported on a slab with fewer supports like a hotel, foyers, or casinos. You need to have a slab which will receive the loads from above, a multitude of loads from above, and transfer them to columns somewhat apart. This is an example where you have a closely spaced supports above, and below the parking has wider supports above. You have a transfer plate here between the two occupancies. This is an interesting example in Macau where over 80 levels of hotel and residential are supported over an 11 feet slab thickness, 3.5 meters, over a casino, and then you have parking below. To cast 3.5 meter slab above 35 meters or 38 meters is a challenge to support. So the construction used 2 layers, and we had a similar construction using 3 layers. The first layer is about 3 feet 1 meter and carries its own weight and reinforcement, the positioning of the layer above. And it is supported on the ground. Now, once the first layer is cast and has adequate strength, then the second layer is cast over it for completion of the work. On the image in the left of the same project, you see the first layer tendon in here and the total height tendon here on the left. On the right is a different project. It's a building construction, is a podium slab that supports over parking, multi-levels of residential occupancy. Now, next we talk about repair and retrofit application of post-tensioning. Post-tensioning can help to add strength when there is a shortfall in strength and correct deflection also. If you have deflection issue in this configuration, an externally applied tendon applies an upward force which can correct the deflection and also adds strength. An application of this I am showing here was in Pier 39, San Francisco, where the parking structure showed larger deflections, and the review of the drawings showed that there was not adequate reinforcement. So external post-tensioning was used. This is a tendon externally attached to one side of the beam stem, and the other side of the beam stem has a similar tendon, which adds strength and also helps with deflection. This is the parking structure. I showed you the image. I see this is another image from the same structure showing the externally applied tendons. At the bottom right, I have view of one of the deviators over the column. The tendons are actually bare unbonded strands going through this concrete tube. Concrete tube was used for fire protection. These are precast concrete, so to say, tubes that house each 7 unbonded strands. Now we move into another application of post-tensioning, and that is to modify the load path. Here, I'd like you to concentrate first on the background to this issue, to this application. Now, let us review how column-supported floors react when they are overloaded. The image shows column-supported floors. Now, if we keep on increasing the load over this slab uniformly applied, eventually it fails. The question is, how does it fail? What would be the shape of a failure? This is one option where there will be folding of each of these panels downward at the middle of the panel and supported over the columns. You develop hinge lines at center line and you have hinge lines over the supports. This is the mode of failure. Now the question is, this is one, and obviously it can possibly fail the other way. It will fail in one of the two. The question I like to raise is, for the mode of failure shown here, what is in the slab that is providing resistance to counteract failure? What is there? You would say the reinforcement that crosses this hinge line over the columns will be stretched, will go into its plastic mode, and you develop plastic moment over the column, and that provides resistance. Also reinforcement which crosses the hinge line at mid point. The moment here at midspan and the moment over the support due to formation of hinge provide resistance. What about the reinforcement in the slab which is going left right over the column? Does the reinforcement going left right over the column contributes in resisting the failure of the slab? The answer is no. It plays no role. I want to conclude that at failure for a symmetrically reinforced slab in both directions, only 1/2 of the reinforcement in the slab contributes to resisting the failure. The other half does nothing. So when will the other half become mobilized? Only if the failure mode is rotationally turned 90 degrees to this. Only if the failure mode is in form of hinge line in up-down direction. Now, that is why when we design column-supported slabs, we design 2 times. For 100% of the load, we'll give us reinforcement in one direction, and 100% of the load reinforcement in the other direction. Now, this is reinforcing what I just mentioned, that the reinforcements over the hinges are mobilized. Now, a project, let me go down next slide and maybe I can work my way back again. There was a project in Southern California, a podium slab post-tension. The engineer did not know that the slab is intended to carry a number of levels of light framing above, thought it's only over parking. During the construction of the structure above, cracks at the bottom, like I show here, developed along with deflection. These cracks signify at midspan shortage in strength. The question was how to fix the problem. Review of the drawings showed that it is correct that the reinforcement to resist the load in one direction is not adequate. But if the reinforcement in one direction and the reinforcement in the other direction, both of them are pulled in to contribute towards resistance, then there's adequate strength. And now the question is how to mobilize the reinforcement in the other direction. To do that, we need to make the failure mode of the slab like what I show here, rather than hinge lines in one direction only, having hinge lines in both directions and also across here. To do this, it is possible if we apply an external force here in the line of columns, between the line of columns, to delay, discourage the point between the line of columns to go down. It was done, it is easy to calculate how much force you need to put between the line of columns from below to stop failure mode as shown on the left and encourage the slab to fail as shown on the right. This configuration mobilizes the reinforcement along these diagonals and in both directions, and it proved to be adequate, and this is what was done for the structure. On the right, I have schematics of the post-tensioning, external post-tensioning, which was used to apply forces upward between the line of columns. Now I move to a different application of post-tensioning. After Northridge earthquake in Southern California, it was noted that buildings that were designed to resist earthquake rightly did resist earthquake and did not collapse. However, a number of them, high-rise buildings, went into post-elastic response. That was considered in design, understood in design, that you go into post-elastic, hinges will form at certain points, but the building will not collapse. Now, if you look at the force displacement at the top of the building resulting from the earthquake, you come up with something like what I am showing here. After the force of the earthquake stops, you end up with a displacement over the height of the building. Depending on the magnitude of displacement, the functionality of some of the installments could be impaired. So the question was how to fix the lack of plumb of a high rise. It's not easy. So a remedy was developed to avoid or to implement a scheme whereby this could be handled. It is based on the image you have on the top right. If you have two columns and a beam, the beam is not attached, it's not glued to the column. It is just resting against the face of the column. And you put an elastic here and you apply a load, and the elastic will stretch. The gap will open. If you remove the load, then the structure tends to go back to its original shape due to stretching, recovery from stretching of this elastic. Now, the gap opens and closes. In addition, another advantage of this model is that if you put a bar across the gap, in going back and forth, the bar stretches, and it can be designed so that it goes into yield. So while the elastic remains, so to say, elastic, the bar goes into yielding and absorbs some energy. So you have two functions: energy absorption targeted, directed to a specific point, and also you have a force for restoration of the deformation of the slab. A detail as shown on the top has been developed where you have the gap here. There's the bar goes across here, and then you have the strands unbonded through a void in the middle. The function or the arrangement is shown schematically like here, and it works when deformed as shown here on the right. You have the gap open here and up there, and you have stretching of bars going into yield. What you see here is a precast frame that is constructed in the fashion I just described. These beams are touching the column but are not integrated into them. And this is the bundle of strands that goes through. This framing is installed on the perimeter of this building in Roseville near Sacramento, in anticipation that as a result of a high intensity earthquake, the frame will help in keeping the building plumb. This is a multi-level building in San Francisco. The frames you see around the perimeter of the building are constructed with the detailing that I just described, with the objective to restore the building in plumb condition. Now, we haven't had a major earthquake after Northridge, when many such buildings are constructed both in northern and southern California to test the response in real earthquake. In the lab, they have responded well, but in real life, we have to wait. Now I move into a different application, interesting application. In New York, if you have a building that you do not plan or you have a location in a building, you do not have to have a multi-level building where your project is. It is permissible that you sell the air above the building. This is a building here. You can sell the air above the building to next door neighbor. So the next door neighbor can use the space above your building. But to be practical, you also provide, in anticipation of selling the air, you provide some supports so that the projection of the neighbor's building over yours can rest over the supports that you provide. This is 55 Hudson Yards in New York, has had such a similar situation. The projection had to be built over the neighbor's roof with over 4 existing columns with capacities provided by the neighbor. Now, after the design was done and the construction was halfway through, it was observed that the total weight of the projection of the building was within the total capacity of the existing columns below. But the distribution was different. In other words, one column was overloaded and the other column not loaded to capacity. The question was, what can be done to change the reactions of the building that is already gone through its architectural and is being constructed? That lots of effort was done. How to redistribute the building's reactions from above to be within the capacity of the existing post-tension solution. The redistribution took advantage of the hyperstatic components of post-tensioning. Many of my colleagues don't look at hyperstatic as a positive contribution of post-tensioning. It is a drag in design, depending on how you design. But in this instance, it was the saver. Look how it works. If you have a cable and you pull it, and the cable is resisted along its side, you develop forces along the side, and obviously you have the forces at the end. What is important? The entire forces are in equilibrium. The pull is in equilibrium with the side forces. This is very, very important property. We need to remember that a cable is always in equilibrium. Pull of the cable is in equilibrium with the side forces. Now, if you have this cable, which I show on the top right, encased in the body of an object and pull it, obviously this is a tendon being pulled. It applies force up and applies force down. The forces that are applied by the tendon are in equilibrium, but the forces change the shape of the container. That is important to observe. The forces are in equilibrium, but they change the shape. If you go and say, I don't want the change of shape, I am going to put a support here and here and here, you restrict the change of shape to be zero. You restrict the change of shape to be zero at the locations where you stop it. Now tell me, there will be reactions at these points to stop the change of shape. What is the property of these reactions? This is important. The property of the reactions is they must add up to be zero. They must add up to be zero because the forces that instigate them, they add up to zero. So the reactions must add up to be zero. What are these reactions called? These are the hyperstatic reactions from post-tensioning. So if I can want these forces to be in certain magnitude and in certain ratio, I can play with the shape of the tendon. Let us see what I do not know what happened here. What happened here? Take no action. Good. I can play with the shape and the magnitude of the force to have forces of my choice. This is now the way it is applied to the building. I have the four supports. I can select a post-tensioning in the shape and force to have the reactions changed as I wish. This is what was done by putting post-tensioning in the walls of the building between level 7 and level 10. And now it goes up many more levels, but it was adequate to put post-tensioning in 3 levels in the configuration that I show. It will generate hyperstatic reactions that when added to the reactions from the load above, they give total supports to be within limits of the foundation provided. This is what was done, and the building now is constructed and is used. Here I show the post-tensioning tendons sticking out at this location, ready to be stressed. Grouted tendons were used, multi-strand. And lastly, the application is in tension tie. That is common. That is common as a tension tie, like what I have shown here. So in summary, I started by flat slab construction, podium slab, beam and one-way slab construction. Then I talked about mat foundation, talked about post-tensioned slab on expansive soil, largest application in the US, talked about industrial slabs, need to be smooth and level, talked about transfer floors, repair and retrofit, then modification of load path was the one before last, and repair and retrofit, modification of load path was a different item. Then I talked about retrofit of Pier 39, correction of seismic deformation, redistribution of reaction was the last item, and the tension tie was the last item. Now the information that I presented is extracted from this book. Thank you for listening and your patience.